Volcanoes are among the most powerful forces ever unleashed on planet Earth. When they erupt, they can reshape continents, wipe out ecosystems, disrupt global climate, and alter the course of human history. Today, we are exploring the most scientifically verified, high-impact volcanic eruptions in the geological and historical record. Events so large they left unmistakable signatures in ice cores, tree rings, ash layers, and written accounts. To understand why these eruptions matter, we begin with the basics. The Volcanic Explosivity Index, VEI, is the scale used to classify eruptions. It ranges from VEI 0, the gentlest lava oozes, to VEI 8, the most explosive events known in Earth's recent history. A VEI 5 eruption can produce ash columns that reach the stratosphere. A VEI 6 can disrupt global climate for months. A VEI 7 can erupt more than 100 cubic kilometers of material. VEI 8 eruptions, the rarest and largest, release over 1,000 cubic kilometers, enough ash to cover entire countries. These eruptions leave long-lasting scientific markers. Ice cores from Greenland and Antarctica contain layers of volcanic sulfate, allowing researchers to pinpoint the timing and magnitude of major ancient eruptions. Tephrochronology, the study of volcanic ash layers, helps connect eruptions to specific regions by analyzing the chemical fingerprint of the glass shards within the ash. Tree ring studies reveal sudden drops in temperature following volcanic winters. Together, these tools form one of the most precise geological timelines available. Our first eruption is one of the largest in the last 2 million years, the Toba supereruption, which occurred roughly 74,000 years ago in what is now Indonesia. Toba was a VEI 8 event, one of the highest categories on the VEI scale, and a type of eruption that only happens perhaps once every 100,000 years. Geological deposits show that Toba expelled an extraordinary amount of material, forming the massive Lake Toba caldera we see today. Ash from the eruption has been identified across the Indian Ocean, India, the Arabian Peninsula, and parts of East Africa. Ice cores from both Greenland and Antarctica show a clear sulfate spike corresponding to this period, indicating that the eruption injected enormous amounts of sulfur aerosols into the stratosphere. These aerosols reflect sunlight and can cause significant cooling. Climate models suggest Toba may have led to global temperature declines lasting several years, with some regions experiencing longer-term climatic disruptions. While early theories proposed that Toba caused a near extinction of early humans, modern genetic research has shown no evidence for a population bottleneck at this time. Instead, the scientific consensus is that the eruption caused substantial, but not civilization-ending, environmental stress. Next, we move to one of the most violent eruptions of the last 5,000 years, the Taupo eruption in New Zealand. Around the year 232 CE, the Taupo volcano produced a VEI 7 event, ejecting more than 100 cubic kilometers of material. This eruption produced pyroclastic flows that devastated the landscape around Lake Taupo and generated ashfall that spread across the southern Pacific. Unlike most eruptions of this scale, Taupo occurred during a period with some historical observation. Ancient Chinese records from around this time report unusually red skies, which some scholars attribute to stratospheric volcanic aerosols from Taupo. Taupo's eruption column is estimated to have reached over 50 kilometers into the atmosphere. The pyroclastic flows were so intense that they stripped vegetation and modified large portions of New Zealand's North Island. Today, the lake that fills the caldera is one of the most studied volcanic systems on Earth, continuously monitored for modern signs of unrest. The eruption's scale and impact make it one of the strongest known volcanic events since the end of the last ice age.
Our next major eruption is the Thera eruption, also known as the Minoan eruption.
which occurred around 1600 to 1500 BCE on the island of Santorini in the Aegean Sea. This eruption is typically classified as VEI 6 or possibly low VEI 7 based on tephra volume estimates. It destroyed much of the ancient settlement of Krakatoa and sent ash across the eastern Mediterranean. Geological studies show that the eruption generated large tsunamis, which likely impacted coastlines throughout the Aegean. The Thera eruption has sometimes been connected to the weakening of the Minoan civilization, but modern archaeological research indicates a more complex picture. While the eruption caused significant regional disruption, the Minoans continued to exist for centuries afterward, and their ultimate decline resulted from multiple factors, including political pressures and later Mycenaean influence. Scientifically, Thera's significance lies not in catastrophic societal collapse, but in the scale of ash dispersal, tsunami generation, and its clear presence in Mediterranean cores and ice core sulfate data. Moving forward in history, we arrive at Mount Tambora, located on the Indonesian island of Sumbawa. Tambora's eruption in April 1815 is the largest confirmed eruption of the last 1,000 years, classified as VEI 7. It produced an ash column more than 40 kilometers high and expelled roughly 150 cubic kilometers of material. The eruption injected massive amounts of sulfur dioxide into the stratosphere, which oxidized into sulfate aerosols. These aerosols encircled the globe, dimming sunlight and cooling the planet. The result was the Year Without a Summer in 1816. Instrumental climate records, as well as tree ring studies in North America and Europe, show an abrupt drop in temperatures. Crop failures occurred across Europe, leading to food shortages and migrations. In North America, frosts struck in June, and snow fell in the northeastern United States during summer months. Tambora's climatic effects also influenced culture. During the cold, dark summer of 1816, Mary Shelley stayed indoors in Switzerland, where she wrote the beginnings of Frankenstein. Before Tambora, another Indonesian eruption shaped world history, Krakatoa, in 1883. This eruption was VEI 6, smaller in volume than Tambora, but extraordinarily violent. The explosions destroyed much of the island complex, produced a tsunami that killed tens of thousands of people, and created atmospheric effects observed around the globe. Barometers recorded pressure waves circling Earth multiple times. Contemporary paintings captured blood-red sunsets caused by volcanic aerosols. Sound waves from the largest explosion were heard over 3,000 miles away. Krakatoa became one of the first eruptions to be globally documented with modern instruments, providing scientists with valuable atmospheric data. Finally, we reach a modern event, the 2022 Hunga Tonga Hunga Ha apai eruption in the South Pacific. Although classified as VEI 5 to 6, it produced the most powerful atmospheric explosion ever measured by satellites. The eruption sent material more than 50 kilometers high and injected an unprecedented amount of water vapor into the stratosphere, a unique effect caused by the eruption occurring underwater. Satellite imagery captured the pressure waves spreading around the planet multiple times. The eruption generated tsunamis detected across the Pacific and disrupted regional communications, but its scientific value is extraordinary. It provided real-time data on how explosive underwater eruptions interact with the atmosphere. With these eruptions behind us, we turn to the future and the systems scientists monitor most closely. Modern volcanology is vastly more advanced than in the past, combining satellite observations, seismology, GPS ground deformation measurements, gas monitoring, and real-time thermal imaging. These tools allow researchers to understand the behavior of large volcanic systems and detect early signs of unrest. One of the most discussed volcanoes is Yellowstone in the United States. Yellowstone has produced 3 major eruptions in the last 2.1 million years, including one VEI-8 event. Today, Yellowstone remains active, but scientific consensus is clear. There is no indication of an imminent supereruption. The volcano exhibits regular hydrothermal activity, ground uplift and subsidence cycles, and frequent small earthquakes, all typical for a large caldera system. Monitoring networks provide detailed insights into the magma chamber's behavior, and no signs suggest abnormal pressure buildup. Another closely observed system is Campi Flegrei near Naples, Italy. This large caldera has a long history of eruptions, including a VEI-7 event approximately 39,000 years ago, known as the Campanian Ignimbrite eruption. Modern Campi Flegrei experiences periodic uplift and seismic activity, but current patterns remain within known historical ranges. Scientists emphasize that while the area is geologically active, monitoring exists precisely to reduce risk through preparedness. Japan hosts several major caldera systems as well, including Ira caldera and Iwo Jima, Ioto, both of which show long-term signs of inflation. These systems are monitored continuously by the Japan Meteorological Agency. Local unrest does not imply catastrophic eruption. Instead, it provides important data on magma movement over long timescales. Similarly, New Zealand's Taupo remains active, but modern measurements show typical background activity rather than immediate concern. Understanding these volcanoes is essential, but equally important is recognizing what the geological record tells us. Large eruptions, VEI-7 and VEI-8 events, are rare on human timescales. While they have occurred in the past and will occur again, modern civilization has unprecedented monitoring, modeling, and hazard mitigation capabilities. Today's science cannot prevent eruptions, but it can provide early warnings, assess likely eruption styles, and help communities prepare. The lesson of Earth's greatest eruptions is not fear, but perspective. The planet has produced extraordinary forces, events capable of altering climate, redirecting human migration, and reshaping continents. Yet humans have repeatedly adapted, reorganized, and advanced, even after these powerful natural shocks. Studying these eruptions gives us insight into how Earth works, how climate responds to sudden changes, and how societies can remain resilient in the face of rare but high-impact natural events. Volcanoes remind us that Earth is always active, always changing, and always capable of surprising us. By understanding the largest eruptions in scientific history, we gain a clearer picture of both our past and the dynamic planet we continue to inhabit. The ground beneath our feet is not static, and history's greatest eruptions are a testament to the immense forces shaping our world. Thank you for watching. Subscribe for more deep dives into the world's incredible histories.